Welcome back. In the last video we have introduced cadmium telluride solar cell technology. We showed the material properties and how doping of cadmium telluride can be achieved. In this video we will continue with the standard cadmium telluride cell structure and we will discuss the production process. This illustration shows the cross-section of a standard cadmium telluride based solar cell with an absorber layer of about 4 micrometers. In contrast with the previous demonstrated CIGS technology, a cadmium telluride solar cell is most commonly deposited in a superstrate configuration. This implies that the contact layer at the top of the structure where the light will enter the solar cell is deposited first. And this layer is therefore required to be transparent. Most commonly forms of n-type doped tin oxide or glass is used. Then, similar to the CIGS cell structure, a thin n-type cadmium sulfide buffer layer is formed by a chemical bed deposition method. This layer forms a heterojunction with the p-type cadmium telluride layer. As was explained in the previous video, doping of cadmium telluride is difficult. By depositing in a superstrate configuration, the interface of the cadmium telluride layer with the metal back contact can be controlled better than in a substrate configuration. For instance, the cadmium telluride layer can be etched chemically before depositing the metal contact, creating a tellurium-rich layer and hereby increasing the doping concentration. Before the actual metal contact layer for lateral conduction is deposited, a contact buffer layer is deposited in the forms of zinc telluride or antimony telluride. This layer will improve the contact quality and has superior stability over the copper containing contact layers that were used in the past. The finer metallic layer is usually made of molybdenum, as this proved to protect the cell from moisture inclusion. When we take a closer look at the energy band diagram of a cadmium telluride solar cell, we can see that the front transparent conductive oxide or TCO layers have a wide band gap of around 3.6 electron volts. Furthermore, we can see that the cadmium sulfide layer has a band gap of 2.4 electron volt, which will form a heterojunction with the p-type cadmium telluride layer with a band gap of around 1.45 electron volts. By creating a tellurium-rich cadmium telluride layer, the material is made heavier p-type doped close to the back contact. This creates a barrier for electrons and these are repelled towards the front of the device while holes will drift towards the back contact. Now that we have discussed the standard structure of a cadmium telluride solar cell, we will look at the production process to deposit and improve the cadmium telluride absorber layer. The usual method for the production of cadmium telluride layers is by closed space sublimation or CSS. Here the substrate and the target are placed in a vacuum chamber on the two graphite electrodes at a distance of a few millimeters. Upon heating the bottom graphite electrode of the target material, it will evaporate and deposit on the substrate, which is kept at a somewhat lower temperature. Most commonly a borosilicate glass is used that can withstand the processing temperature of 650 degrees Celsius. This will result in the best quality cadmium telluride layer. The alternative is to use soda lime glass, which is also used for the CIGS solar cells. Another method to produce a high-grade cadmium telluride layer is by vapor transport deposition or VTD. In this process, the semiconductor material in powder form is sublimated and fed into a reactor together with a carrier gas. Inside the reactor, the temperature of the saturated mixture is increased by an electric heater. The glass substrate will then be slowly passed under the reactor on a conveyor. The heated vapor can pass through a permeable membrane and reach the deposition opening when it comes in contact with the substrate at a lower temperature. Now the mixture of semiconductor vapor and carrier gas will be supersaturated, which will result in a film growth on the substrate. There are other methods available to produce cadmium telluride layers, such as electrodeposition or physical vapor deposition. We will now discuss a special process step that is crucial in obtaining a high efficiency cadmium telluride cell. As deposited cadmium telluride layer does not as such have good electronic properties, since it has many point defects, extended defects and unpassivated grain boundaries. A treatment by cadmium chloride was introduced in the late 70s, and with this process the conversion efficiency could be improved from several percent to above the 10% in those days. It is sometimes called the magic treatment, since it's still not completely understood which mechanisms play a role in improving the electronic properties. X-ray diffraction measurements have shown that after the cadmium chloride treatment at a temperature of about 250 to 400 degrees Celsius, recrystallization occurs, increasing the grain size. At the same time, the grain boundaries will be better passivated by chlorine diffusion. Another well-accepted mechanism is that the interface between the cadmium telluride and cadmium sulfide buffer layer will mix and form cadmium tellurium sulfide compounds. These layers will provide a better lattice message going from the cadmium sulfide to the cadmium telluride. Finally, it's observed that the p-type doping of cadmium telluride is increased, presumably by cadmium vacancies and chlorine atoms on tellurium sites. In these two video lectures, we have discussed the optoelectrical properties of cadmium telluride materials and how the doping is achieved for this technology. The typical cell architectures used for cadmium telluride PV technology were also presented. Finally, the processing methods have been introduced. In the next videos, we will dive into the PV technologies based on organic materials and perovskite materials. So, see you back in the next video.